Okay, this video we're going to talk about Laplace transform. So this is the definition. This is a definition of Laplace transform. So Laplace, so this L, Laplace, by the way, is a mathematician. So he invented this. So this L represents the Laplace transform. It transforms f of t. So this lowercase f the variable is t, transform this to be f of s. Okay, the definition is this. It's an improper integration, e to the negative st. Okay, we see the variable for capital F here. And t is a variable corresponding to this dt. Okay, so this is the definition of Laplace transform. Let's just go through a couple of examples. So the first example is we want to find the Laplace transform of the constant function. Right? We use 1 as an example. It could be 1, could be 2, could be some other numbers. Basically, how Laplace transform a constant function. And we want this t to be at least 0. So we just use the definition. Right? Laplace transforms 1. So this f of t is 1. Transform 1. Then we use the definition, right? E to the negative st, well, f of t is 1. Is 1. So we have this, the integrand becomes just e to the negative st. So we integrate improper integration, we use a limit, idea of limit, we use a dummy variable b. Then we do the calculation, we integrate, get this, then take a limit of this. So in the end, we get a 1 over s. So Laplace transforms constant function of 1 to 1 over s. All right, s we want to be a positive number. So this is 1. 1 Laplace transform. This is the second example. So exponential function e to the at. Exponential function e to the at. A is just some constant, some numbers. Okay, e to the at. Again, we use the definition. So Laplace transform the e exponential function into this is the integrand. We have e to the negative st times e to the at, because this is our function transfer. And base e, same base, we just add the exponents. So we get e to the negative s minus at dt. Right? So we integrate that, we get this, get negative 1 over s minus a e to the negative of s minus a of t. Then we evaluate from t to 0, t to the infinity. Of course, we needed to use the idea of limit. Right? We use a dummy variable b to see this. So same idea. So we have two cases. Right? If s minus a is greater than 0, if s is bigger than a, then the limit, we take the limit, it goes to 0. If a is greater than s, if the constant a is bigger than s, then the limit goes to infinity. Okay, so if s equals to a, so that means that s minus a equals 0. Right? If s minus a equals 0, that's just 1. The integration is just 1. It also goes to infinity. So the only thing makes sense is for s greater than a. So when we take a limit, so in the end, we get this. So Laplace transform e to the at for s greater than a, we get a 1 over s minus a. So that's for exponential Laplace transform exponential functions into a rational function. So this is a second example of Laplace transform. Yeah, let's do one more. Let's do polynomials. Let me resolve this. So let's see, f of t is t to the eighth power, and a will want to be greater than -1. And so Laplace transform t to the a. We use the definition again. Right. Use the definition. Now we need to, so we have e to the -st, t to the eighth power. So we need to do some substitution. So we let u be st, or t equals to u divided by s. Then du is just s dt. So 1 over su is dt. Then once we have this, we just substitute everything into u and s. So we get this. Then we keep doing the calculation, right? Again, of course, we want to use the just being ignored here. The marvelous things happen here. We say e to the -u, u to the a du. This is the definition of gamma function. Gamma function. So Laplace transform t to the eighth power, just gamma of a plus 1, right? You could think of this as a factorial divided by s raised by a plus 1. So this is the third Laplace transformation, right?